One of the most important and useful things that you can do in your engineering and science classes is to do a dimensional analysis. It can help us really understand a problem. It can help us understand what an equation looks like, how to use it, how to come up with an equation. It can help us understand the problem or the situation. It can help us understand whether our answer is correct or to check our work as well. In the video that we talked about what are dimensions, we talked about speed and how speed is made up of a length divided by time. And just by looking at this, we can see some really important things. Number one, if I want to solve for any one of these, I need to know two things, and then I can solve for the third. So if I know speed and length, I can solve for time. If I know length and time, I can solve for speed. And if I have time and speed, I can solve for length. The second thing I know is that if I don't have this specific equation and they want me to use some other equation and I'm not sure which one to use, I can look at it and see which one of these equations has a length over a time in it, and then I know that I'm getting something like speed. Lastly, I also have to make sure I plug in the numbers correctly. My length always goes on the top, my time always goes on the bottom. So here's another example. In math class, we have the equation of a line, y equals mx plus b. And the y is going to be the output, m is the slope, x is the input, and b is our starting point or our intercept. So I have this equation. I came up with this one just off the top of my head. It's not a great problem or anything. A drive-in movie theater charges $5 per car that comes in. So that's the base price. A car comes in, it costs $5. Then they count up the people in the car, and each person in the car costs $2 more. So below, I have an equation that shows the total price. I have the cost, C, equals $2 per person, times P, which is my number of people, plus $5 for the car. So what we can do is we can really break this down dimensionally. Now, before we move any further, I want to talk about a side note here. There's a saying that says you can't add apples and oranges. What this really means is you can't add two dissimilar things. In this case, we can't add together different dimensions. I can't take something like a temperature and a time and add them together. It just can't be done. And so one thing that we can do is we can see, does this equation even make sense? Am I adding all like things together? In the case of this problem here, every single term should be the same dimension. And so I like to start with my answer because I know what I should be getting. And that's my cost over here. My cost, that should equal some stuff. So this side of the equal sign, my left side of the equal sign is a cost, which means the right side of my equal sign also has to be a cost. Now when I go to the right side of my equal sign, I also notice that I'm adding some stuff together. And if I can only add like dimensions, that means that this first term has to be a cost, and this second term has to be a cost. I can definitely see that this second term is a cost. But what about this term here, this $2 per person times the number of people? I definitely see that there is a dollar sign there, which means that there is a cost involved, but I can't have a cost with other stuff. It strictly just has to be a cost. And so what we have here is I have $2 per person. And if I multiply that by a person, if I can spell person or number of people, my people or my persons cancel out, which leaves me just with the cost. And so what this really breaks down to is I have a starting cost, and then depending on my number of people, I might have an additional cost as well. Those two things sum together, my starting cost plus my additional cost equals my total cost. So this is a valid equation. Everything's cost, I'm adding it together, and it's going to give me the answer that I want as long as I plug things in correctly.